Let's take a look again at the definition of almost sure convergence. We say that a sequence of random variables xn converges almost surely to x, to random variable x, if and only if the limit of xn of omega is x of omega for any omega in the sample space. Right? Well, for almost every omega in capital Omega. And from this we can observe, call omega 0 the set of events such that the lim sup of xn of omega is equal to the lim inf of xn of omega. Then xn converges almost surely to x if and only if the probability of omega 0 is 1. So if and only if omega 0 is an almost sure event, and now we see again the theorem that characterizes almost sure convergence. Characterization of almost sure convergence. A sequence xn converges almost surely to x if and only if the sum over n of the indicators of I epsilon, which recall it's defined in this way. I epsilon is the indicator on the interval epsilon plus infinity, which is 0 when x is smaller than epsilon and 1 when x is larger. So this, applied to the difference xn minus x, converges. It's fine. It's fine. It's finite. Almost surely. Let's go with the proof. So, assume xn converges almost surely to x. I don't know why I have put the parentheses here. Then write yn to be the absolute value of xn minus x, and observe that for any omega in omega 0, from the analogous result of real sequences that we have seen, we have that this sum is finite. For any epsilon greater than 0, and therefore this thing here, which we call asterisk, holds. Now, for the other implication, assume that asterisk holds. And consider epsilon k strictly decreasing to 0 as k goes to infinity, decreasing to 0 as k goes to infinity. Well, this is implicit in some way. And let nk be the sum over ni epsilon applied to the difference xn minus x. Then we have that the probability of nk being finite is 1. Is 1 for any epsilon greater than 0 because of this. Because this holds. And this is not for any epsilon but for any k. Now observe that epsilon k plus 1 is smaller than epsilon k, meaning that nk, well I epsilon k plus 1 is smaller than I epsilon k, which in turn implies that nk is, well, nk plus 1 is greater than nk. And consider the events, and consider the events in which nk is finite. For any k. And observe that the sequence of such events decreases with k. Decreases with k. So what can we say now? The intersection of these events, k finite, is the set of outcomes in which the sum over ni epsilon applied to xn minus x is finite. This is by definition of nk, and this is for any epsilon greater than 0. But this is nothing but omega 0. Why? I don't know. In any case, the probability of omega 0 is 1 because, well, this is the probability of the event limit over k of nk finite, let me write it a bit better. And this we have now, by the continuity of the probability measure, by sequential continuity of the probability measure P, we can say that this is the same as the limit of the probability of nk finite, which is 1 as we have seen. Therefore, for any omega in omega 0, xn of omega, converges pointwise or eventwise, well, of outcome-wise, let's say, to x of omega. E punto. Let's try to recap. So, for the first part, we assume almost sure convergence and show this by means of the result of the convergence of real sequences. And on the other hand, what we do is we assume this, we consider a decreasing sequence of epsilons, this should be epsilon k in my opinion, because it should depend on k. So the indicators are smaller and smaller, or no, we actually keep the indicator fixed, we just let k go larger and larger. This will require some more review, but with this, let's keep going now. Let's go with a lemma, which is Borel-Cantelli 1. I call it like this. This is the first Borel-Cantelli lemma, and it says that given a sequence Hn, given a sequence of events, if the sum over n of the probabilities of Hn is finite, then the number of times in which these events happen is also finite. Almost surely. And we can also write this in the following alternative ways. Probability of Hn infinitely often equal to 0. Probability of the lim sup n of Hn equals 0. And for this, if you want, you can see Schindler's book at page 101. How can we interpret this result? This result, well, the Borel-Cantelli lemmas are used usually to prove almost sure convergence. And in this case, we have that if the probabilities do not diverge, which means the events become rare, more and more rare, so the probability is smaller and smaller, then they will not happen infinitely many times, because the probability becomes so small that at some point we basically will have that they happen from time to time, but in a finite number of times, let's say, I don't know. Like, we can think of this, I remember one interpretation of this can be in terms of world records. So breaking a world record is more and more challenging. So we can say that the probability of breaking a world record is smaller and smaller. And so this will imply that the number of times in which our record will be broken is finite. And the proof is simply an observation, which I don't remember. Denote the sum over n of these indicators and call it n, and recall that indicators are actually Bernoulli random variables, if you want. So the expectation of n, this is the sum of Bernoulli random variables, and the expectation of n is n. No, it's the sum of the probabilities. Why? Because the expectation of a Bernoulli random variable is the probability. If you recall, let's say xn Bernoulli is 1 with probability p and 0 with 1 minus p, and so the expectation of xn, well, of x, is 1 with probability p plus 0, 1 minus p, but this is 0, so this cancels out, and this gives p. And so for this, we basically sum, and we do not require independence here. This is important. And the claim becomes that if the expectation of n is finite, then n is finite, or vice versa. Let me think. It should be like this, right? Yes, almost surely. But this is obvious because of the definition of the expectation. So the expectation is finite if the random variable is finite. And this is a property by definition of the expectation, because if you recall the expectation of a random variable x, which is this thing, blah blah blah, is finite if and only if x is finite. Okay, now let's take a look at the proposition. If there exists if the sum over n of the okay, so this is useful. This is useful because this is what we usually use in exercises, I think. If the sum of the probabilities of xn being deviating from x by a value larger than epsilon is finite, then xn converges to x almost surely. This is important. This is for any epsilon. For any epsilon greater than 0 should be. For any epsilon greater than 0. And let's take a look at the proof. So consider Hn events of this form, or call simply Hn to be the difference between x and x larger than epsilon. So these events. Then the probability Hn, no, then the sum over n of the indicator of these events what can we say is finite. Why? By the first Borel-Cantelli lemma. I think yes, and this implies that xn converges almost surely to x. No, this is by the characterization theorem for almost sure convergence. By the characterization theorem of almost sure convergence. How can we call it? Characterization theorem for almost sure convergence. We can call it characterization of almost sure convergence. Well, CT, characterization theorem for almost sure convergence. This is important, and it is so important that I will write it again. So if the sum over n of the probability that xn minus x in absolute value is larger than epsilon is finite for any epsilon greater than 0, we have that xn converges to x almost surely. Now we have another proposition. If there exists a sequence epsilon n decreasing to 0 such that the sum over n of the probability that the difference between xn minus x is greater than epsilon n is finite, then xn converges to x almost surely. Which is quite similar, but this time we consider a sequence of epsilons, which decreases to 0. So this is similar to this, I think. Oops. And we have a further proposition. If there exists a sequence epsilon n such that the sum of the epsilon n's converges and the sum over n of the probability that the difference xn plus 1 minus xn is larger than epsilon n is finite. Then xn converges almost surely to x. And this is again an alternative way of seeing the same result, basically. I think. No, because this time we are considering subsequent, I don't know how to call them, like consecutive terms here. Now we are ready to state the Borel-Cantelli lemmas together, and this will probably conclude for today. Borel-Cantelli lemmas. They say the following: let Bn be a sequence of Bernoulli random variables, then Bernoulli well, if the sum over n of the expectation of Bn is finite, this implies, this is basically the first Borel-Cantelli lemma rephrased in terms of Bernoulli random variables. Then we have that the sum of the indicator of, well, the sum of the Bn, so the sum, like we consider this, Bn is 1 if it happens, the Bernoulli random variable, if it happens, is 1, if it doesn't, if it takes value 0, we just sum 0. So if this sum is, well, this sum will be also finite, almost surely. And this is the first part. And the second part says that if Bn are pairwise disjoint, well, pairwise independent, we have that the sum of the Bn is actually infinity, so they happen infinitely many times, almost surely. And for the proof of the divergence part, well, let's do it. It's not too long, it's a bit tedious, So proof of the divergence part. So proof of 2. Call Pn the expectation of Pn. And An the sum of the expectations. Bi for I from 1 to n. Which in other terms is the sum from 1 to n of Bi. And we also define Sn as the sum of the Bi's. Bi. And S is the limit of Sn. So we define all these things. First, we have that the variance of Sn, which is the sum of the variances since they are independent, this is the variance of Pi is Pi times 1 minus Pi, which is less than the sum of Pi, which is An. We defined it to be An. Second, fix B in the interval 0 plus infinity. We know An is increasing to infinity. By hypothesis, because why? So we assumed here this and we are trying to prove this, or what? Well, then also we have that An over the square root of B times An is increasing to infinity, and then the event S being finite is the limit of things, is the limit of the increasing sequence S being less than An minus square root of B times An. And since Sn is less than n, is less than S for any n, this implies that I think there is a typo here, because I basically wrote the same thing and it should be Sn. I don't have pencil. Let me try to correct. It should be like this. Since Sn is less than S, we have that the event Sn event S being less than an minus square root of ban. Now, question. Why do we consider the square root of ban? I don't know. But we know here that this contains Sn less than an minus square root of ban. And next, we also have that the set or the event Sn less than an minus square root of ban is contained in the following event. Absolute value of Sn minus an less than square root of ban. Actually larger. And now the probability of the event S less than an minus square root of ban this thing is less than the probability of Sn less than an minus square root of ban. Which is in turn bounded above by the probability that the difference in absolute value between Sn and an is greater than the square root of ban. And taking the lim sup, what we obtain is that the lim sup of the probability that S is less than an minus square root of ban is less than the limit supremum of the probability that the difference in absolute value between Sn and an is greater than the root of ban. And applying Chebyshev, gives oh, okay, well, I skipped one part. Damn. Taking the rim soup, this is this. Okay, the left hand side is this thing, taking the rim soup, blah blah blah. Oh no, taking. Okay, wait. I'm making confusion here. For the final part, I think we will see it next time. Okay, let's finish it here.